the summer of 1950, 4 physicists walked to lunch. They were at Los Alamos National Laboratory, the place where the atomic bomb had been built 5 years earlier, and the dining hall was inside Fuller Lodge, a log and stone building that still stands today. The 4 men were Enrico Fermi, who had won the Nobel Prize in Physics in 1938, Edward Teller, who would later be called the father of the hydrogen bomb, Emil Konopinski, a theoretical physicist, and Herbert York, who would go on to become the first director of Lawrence Livermore National Laboratory. These were not small minds. These were 4 of the most brilliant physicists alive, walking across a patch of New Mexico desert to get lunch. On the way, they were joking about flying saucers. A cartoon had just been published in The New Yorker on May 20th, 1950, drawn by Alan Dunn. It showed little green men with antennae stealing trash cans off the streets of New York City and loading them onto flying saucers parked in Central Park. There was no caption. The joke was that 2 unexplained phenomena had been in the news that summer: reports of unidentified flying objects and mysteriously disappearing trash cans in Manhattan. The cartoon proposed a single explanation for both. Fermi apparently found this hilarious. He told his colleagues it was a reasonable theory because it accounted for 2 distinct phenomena. The conversation drifted to whether faster-than-light travel was possible. Teller estimated the probability of seeing a superluminal object within the next 10 years at 1 in a million. Fermi thought that was far too low. He said the real probability was closer to 10%. Then the conversation moved on. They sat down. They started eating. And then, in the middle of lunch, with no warning and no connection to whatever they had been discussing, Fermi suddenly blurted out a question. The 3 surviving companions each remembered it slightly differently. Teller recalled it as, "Where are they?" York remembered, "Don't you ever wonder where everybody is?" Konopinski, whose version is the one that stuck, recalled the most famous version. "But where is everybody?" Fermi wasn't joking anymore. He grabbed a napkin and started doing calculations, back of the envelope stuff, the kind he was famous for. How many stars in the galaxy? How many might have planets? How old the galaxy is? How long it would take a civilization even slightly more advanced than ours to colonize the whole thing? His conclusion was fast and unsettling. Earth should have been visited long ago and many times over. The galaxy is roughly 13.6 billion years old. If habitable planets formed around stars just 1 or 2 billion years after the Big Bang, civilizations could have had an 8 billion year head start on us. Even at speeds well below light, you could colonize the entire Milky Way in 5 to 50 million years. That sounds like a long time until you realize it is less than 0.5% of the galaxy's age. Fermi's math said the galaxy should be crawling with intelligent life, but it isn't, or at least it doesn't look like it is. Leo Szilard, the Hungarian physicist, reportedly cracked a joke when he heard about the conversation later. They are among us, but they call themselves Hungarians. But Fermi wasn't laughing. His question has haunted physics, astronomy, and philosophy for 75 years. It has a name now, the Fermi Paradox, and despite generating hundreds of published papers, at least 75 formally proposed solutions, an entire career spent searching the sky for signals, nobody has answered it. Think about the numbers for a second. The Milky Way contains somewhere between 100 billion and 400 billion stars, about 7% of those are Sun-like G-type stars, which gives you 7 to 28 billion stars, roughly similar to our own. 3/4 are M-dwarfs, red dwarfs, which also appear capable of hosting habitable planets. In 2020, a team led by Steve Bryson at NASA published a paper in the Astronomical Journal, estimating that there are at least 300 million potentially habitable planets orbiting Sun-like stars in our galaxy alone. Upper estimates go as high as 2 billion. A separate study from the University of British Columbia by Michelle Kunimoto and Jamie Matthews calculated up to 6 billion Earth-like planets around G-type stars. The nearest one is probably within 20 to 30 light years. Astronomically speaking, that is next door. We know the planets are there. The Kepler Space Telescope, launched in 2009, confirmed that virtually all stars have planets. The fraction with planets, which Frank Drake could only guess at in 1961, turns out to be essentially 1.0. Planets are not rare. Habitable zone planets are not rare. The galaxy has been around for over 13 billion years. The ingredients for intelligent life have been available for most of that time. And yet, after more than 60 years of searching, since Project Ozma first aimed a radio telescope at 2 nearby stars in 1960, we have found exactly 0 confirmed signals from extraterrestrial intelligence, 0 artifacts, 0 megastructures, 0 probes, 0 visits. Where is everybody? 11 years after Fermi's lunch, on November 1st, 1961, about 12 scientists gathered at the Green Bank Observatory in West Virginia for the first formal conference on searching for extraterrestrial intelligence. The meeting was organized by J. Peter Pearman and a young astronomer named Frank Drake, who would live until September 2nd, 2022. The attendees were remarkable. Philip Morrison, the physicist who had co-authored one of the first papers proposing radio SETI. Melvin Calvin, a chemist who actually received his Nobel Prize phone call during the meeting. Joshua Lederberg, a biologist. John C. Lilly, the neuroscientist famous for his work on dolphin communication. Barney Oliver, the radio engineer from Hewlett-Packard, and the youngest person in the room, a 27-year-old postdoc named Carl Sagan. Drake wrote an equation on the blackboard. It was meant as an agenda for the meeting, a way to organize the discussion, not a rigorous calculation, but it became the most famous equation in the history of the search for extraterrestrial life. N equals R star times F sub P times N sub E times F sub L times F sub I times F sub C times L. The number of detectable civilizations in the galaxy equals the rate of star formation times the fraction of stars with planets times the number of habitable planets per system times the fraction where life develops times the fraction where intelligence develops times the fraction that develop detectable technology times how long those civilizations remain detectable. Drake's original estimates from that meeting placed the star formation rate at 1 per year, the fraction with planets between 0.2 and 0.5, the number of habitable planets per system between 1 and 5. He and his colleagues assumed that life, once conditions allowed it, was nearly certain to develop. Same for intelligence. Their conclusion was that the number of detectable civilizations in the galaxy was roughly equal to L, the average lifetime of a technological civilization. Optimistic estimates put L in the millions. Their range for N was between 1,000 and 100 million civilizations. Drake's personal best guess was about 10,000. Those were the numbers that made the silence so strange. If even Drake's most conservative estimate was right, there should be 1,000 civilizations out there, many of them millions of years older than us, and we should have heard something by now. The galaxy is not that big. Light crosses it in 100,000 years. Radio signals travel at the speed of light. If a civilization on the other side of the Milky Way had started broadcasting 1 million years ago, their signals would have washed over Earth 900,000 years before humans existed. We should be swimming in alien signals, but we're not. So for 75 years, very smart people have been proposing explanations for the silence, and every single explanation has a problem. The first and maybe most famous is the rare Earth hypothesis. In 2000, paleontologist Peter Ward and astronomer Donald Brownlee published a book called Rare Earth: Why Complex Life is Uncommon in the Universe. Their argument was that while microbial life might be common, complex multicellular life requires an extraordinarily specific set of conditions. You need a stabilizing moon to prevent catastrophic axial wobble, a strong magnetic field to shield against radiation, plate tectonics to regulate atmospheric carbon dioxide, a gas giant like Jupiter in the outer system to sweep up asteroid impactors, the right type of star in the right part of the galaxy, at the right time in cosmic history. Stack all of these requirements on top of each other, and maybe Earth-like complexity is vanishingly rare. It is a serious argument from serious scientists. But the more exoplanets we find, the harder it gets to sustain. 300 million potentially habitable planets is a lot of planets. Even if the odds of complex life on any one of them are 1 in 1 million, that is still 300 planets with complex life in our galaxy alone, and 1 in 1 million might be far too pessimistic. We simply do not know. Rare Earth explains the silence only if life is so extraordinarily rare that we are literally the first. And we are first in a 13.6 billion-year-old galaxy with hundreds of billions of planets is a very strong claim. The second major explanation is the Great Filter, proposed by economist Robin Hanson at George Mason University in 1998. Hanson's logic was elegant and disturbing. Somewhere between dead matter and a galaxy-colonizing civilization, there must be at least one step that is astronomically improbable, some filter that almost nobody gets through. The question is whether that filter is behind us or ahead of us. If it is behind us, if the hard part was abiogenesis, or the jump from prokaryotic to eukaryotic cells, or the evolution of multicellular life, then we are rare but safe. We already passed the test. But if the Great Filter is ahead of us, if civilizations tend to destroy themselves with nuclear weapons, or artificial intelligence, or engineered pandemics, or some technology we haven't invented yet, then we're in serious trouble. Hansen pointed out something chilling. Finding evidence of past microbial life on Mars would actually be bad news for humanity, because it would mean the early steps of life are not that hard, which would push the filter forward in time ahead of us to some civilizational catastrophe that claims everyone. The Great Filter is a compelling framework, but it identifies the problem without solving it. It tells you there must be a bottleneck without telling you where it is. and it requires that the filter be almost perfectly effective. If even 1% of civilizations survive whatever the filter is, the galaxy should still be full of survivors. You need a filter that kills essentially everyone, every time, across billions of years and trillions of planets. That is a lot to ask. The third explanation is the zoo hypothesis, proposed by MIT radio astronomer John Ball in 1973 in a paper in the journal Icarus. Ball suggested that extraterrestrial civilizations know about us, but deliberately maintain non-interference, treating Earth like a wildlife preserve. It is a charming idea, and it has the virtue of being hard to disprove. But it has a fatal structural flaw. It requires universal agreement. Every single civilization in the galaxy, across billions of years and vast distances, has to independently decide not to make contact. A single defector breaks the silence. One species, one rogue individual, one accidental signal leak, and the zoo collapses. Universal compliance among potentially millions of independent civilizations is not a strong foundation for a hypothesis. The fourth is the dark forest theory, which comes not from a scientist, but from a novelist, Liu Cixin, in his 2008 novel, The Dark Forest, the second book in his Remembrance of Earth's Past trilogy, proposed that the universe is like a dark forest full of armed hunters. Every civilization is a potential threat. You can never truly know another civilization's intentions. And because civilizations grow exponentially, even a weak one today could be a dangerous one tomorrow. The rational strategy, Liu argued, is preemptive destruction. Kill them before they can kill you. Stay silent or be annihilated. It makes for extraordinary fiction. As game theory, it has been seriously discussed by academics. David Brin explored similar ideas in his 1983 paper, The Great Silence. But the dark forest relies on worst-case rationality that many game theorists find unstable. It assumes no civilization ever develops reliable communication or trust. It assumes offense always dominates defense. It assumes everyone independently arrives at the same paranoid calculus. And it assumes none of the civilizations that have had an 8 billion year head start on us have found a way to solve the cooperation problem. Humans solved it on a planetary scale in a few thousand years. A civilization with 1 million years of experience might find it trivial. There are more explanations. Sebastian von Herner estimated that the average civilization lasts only about 6,500 years before self-destructing or stagnating. Michael Hart, whose 1975 paper actually formalized the colonization argument often attributed to Fermi, concluded flatly that we are alone. Frank Tipler argued in 1980 that any advanced civilization would build self-replicating probes called von Neumann machines, and their absence proves nobody is out there. Some suggest aliens are broadcasting on frequencies or using technologies we cannot detect, that we are searching a tiny corner of an enormous cosmic haystack. Every one of these explanations requires something extreme, that life is impossibly rare, that everyone dies, that everyone agrees to hide, that everyone destroys each other, that nobody has ever built a single detectable artifact in 13 billion years. Pick any one of these and really push on it, and you find yourself making increasingly heroic assumptions. But here is what almost nobody notices. Almost every proposed solution to the Fermi Paradox shares a single hidden assumption. They all assume that advanced civilizations expand outward. Think about it. The rare Earth argument is about why there are not enough civilizations to fill the galaxy. The great filter is about what stops them from filling the galaxy. The zoo hypothesis is about why they choose not to reveal themselves as they fill the galaxy. The dark forest is about why they kill each other while trying to fill the galaxy. Even the communication incompatibility argument assumes they are out there, in space, doing things at a galactic scale. The default assumption baked into the Fermi Paradox since Fermi first did his napkin calculations is that intelligence expands, that it reaches for the stars, that the natural trajectory of technology is outward, bigger, more energy, more space, more territory. This assumption has a name, the Kardashev scale. In 1964, Soviet astrophysicist Nikolai Kardashev published a classification system in Astronomicheski, journal ranking civilizations by energy consumption. A Type 1 civilization harnesses all the energy available on its planet, roughly 10 to the 16th power watts. A Type 2 harnesses the entire output of its star, roughly 10 to the 26th power watts. A Type 3 harnesses the energy of an entire galaxy, roughly 10 to the 36th power watts. Carl Sagan later added decimal interpolation. Earth currently rates about 0.73 on Sagan's scale. Michio Kaku estimates we might reach Type 1 in 1 to 200 years. The Kardashev scale sounds scientific. It has numbers and exponents, and it appears in serious journals. But it is also an assumption disguised as a classification. It assumes the trajectory of civilization is upward in energy consumption, bigger, more, outward. And in 1964, that assumption felt obvious. The space age was underway. Humans had just started launching rockets. The future looked like science fiction. Space stations, interstellar travel, Dyson spheres. Freeman Dyson had published his famous paper in 1960, just 4 years before Kardashev. Search for artificial stellar sources of infrared radiation in the journal Science. Inspired by Olaf Stapledon's 1937 novel Star Maker, Dyson envisioned a civilization disassembling planets to build a swarm of orbiting structures around a star, capturing all of its energy output. He estimated that a civilization with just 1% annual energy growth would need such a structure within about 3,000 years of industrialization. In a 2003 interview, Dyson called the paper a little joke and noted, "You get to be famous only for the things you don't think are serious." But the concept stuck. It became the archetype of what advanced civilizations should look like: big, visible, consuming stars. And that is the assumption, the expansion assumption, the idea that the natural destiny of intelligence is to grow outward, to consume more energy, to build bigger things, to colonize more space. It is so deeply embedded in the Fermi Paradox that most people do not even realize it is an assumption. It feels like a law of nature. But what if it is wrong? In 2000, at a Foresight Institute gathering called Confronting Singularity, a futurist with an unusual background presented an idea he claimed he had first imagined in middle school in 1972, when he was about 12 years old. His name was John Smart. He held a business degree from UC Berkeley, had completed 2 years of medical school at UC San Diego, studying under James Greer Miller, the systems theorist who had himself studied under Alfred North Whitehead. After med school, Smart had co-founded a company called hyperlearning that prepared students for the MCAT. It grew to 50 employees and served about 3,000 pre-med students across 5 UC campuses before he sold it to the Princeton Review in 1996. Then he went to the University of Houston to study futures at the oldest future studies program in the world, founded in 1975. He was not an astrophysicist. He was not a physicist at all. He was a futurist with a biology background who had spent years thinking about where technology was headed. And what Smart proposed was the precise opposite of the Kardashev scale. He published the first version of his idea in June 2002 in the Journal of Evolution and Technology under the title Answering the Fermi Paradox, Exploring the Mechanisms of Universal Transcension. The definitive peer-reviewed publication came a decade later, in 2012, in Acta Astronautica, the Journal of the International Academy of Astronautics, published by Elsevier. The paper was called The Transcension Hypothesis. Sufficiently advanced civilizations invariably leave our universe, and implications for METI and SETI. The argument was simple and radical. Civilizations do not expand outward into space. They compress inward toward ever smaller, denser, more computationally efficient scales of reality. And they keep compressing until they reach a kind of optimal computational substrate that looks, from the outside, like a black hole. They do not colonize the galaxy. They do not build Dyson spheres. They do not send radio signals or launch probes. They miniaturize. They densify. They vanish. Smart called this trend STEM compression, where STEM stands for space, time, energy, and matter. His definition was precise. STEM compression is the phenomenon whereby the most complex systems in the universe at any given time use progressively more spatially localized, miniaturized, and informationally efficient sets of physical resources to create new versions of locally dominant adaptive complexity. That is a mouthful. In plain language, it means the leading edge of complexity always packs more capability into less stuff. The trend is not outward, it is inward. Our destiny, Smart wrote, is density and dematerialization. Now, you might hear this and think it sounds like philosophical speculation dressed up in a technical language. And Smart himself acknowledged the risk. He admitted in 2017 that his paper had received only a handful of citations and, to my knowledge, no published critiques, and speculated this might be because the hypothesis rests on a series of speculative assumptions about universal evolution and development, and because he is a futurist, not an astrophysicist. Fair enough, but here is why the Transcension Hypothesis deserves serious attention. It is the only proposed solution to the Fermi Paradox that does not require civilizations to be rare, dead, hiding, or hostile. It says civilizations are abundant. Intelligence is everywhere. The reason we cannot find it is not because it failed, but because it succeeded. Every advanced civilization found something better than outer space and moved there. And the direction it moved is not speculative philosophy. It is a trend you can measure. Look at the last 60 years of computing. On April 19th, 1965, Gordon Moore, then Director of Research and Development at Fairchild Semiconductor, published a paper in Electronics magazine called Cramming More Components onto Integrated Circuits. He predicted the number of components per chip would double every 12 months. He projected about 65,000 components by 1975. The actual count for new memory chips that year was 65,536. He was accurate to within a single percentage point. In 1975, he revised the doubling time to every 2 years. Caltech professor Carver Mead gave it the name Moore's Law. The trajectory that followed is staggering. The transistor was invented on December 23, 1947, at Bell Labs. Jack Kilby demonstrated the first integrated circuit on September 12, 1958, at Texas Instruments. Feature sizes on chips shrank from roughly 50,000 nanometers in the 1960s to below 1,000 nanometers in the 1980s. By the early 2000s, they were at 100 nanometers. As of late 2022, TSMC was producing chips at 3 nanometers. In 2025, both TSMC and Samsung are targeting mass production at 2 nanometers. Using gate-all-around nanosheet transistors, TSMC has announced plans for 1.6 nanometers by 2026. The Intel 4004 processor from 1971 had 2,300 transistors. By 2010, chips had crossed 1 billion. Today, they have tens of billions. The feature size has shrunk by a factor of more than 100,000 in 6 decades. That is not expansion. That is compression. Relentless, measurable, 6-decade-long compression. More computation in less space, using less energy, on less material. And it is not just transistors. Jonathan Koomey at Stanford published a study in IEEE Annals of the History of Computing in 2010, showing that the number of computations per joule of energy dissipated doubled approximately every 1.57 years from 1946 to 2000. The R-squared value was above 98%. That is an extraordinarily clean trend, sustained over more than half a century. Since 2000, the pace has slowed to about every 2.6 years, which Koomey linked to the end of something called Dennard scaling, which is the principle that power density stays constant as transistors shrink. That broke down in the mid-2000s. But even at the slower pace, energy efficiency is still doubling roughly every 2.5 years. Richard Feynman identified in 1985 that there is a factor of roughly 100 billion in theoretical improvement still available in how much energy we use per computation. We are nowhere near the physical limits. Smart pointed out that this trend is not unique to electronics. It extends back through the entire history of life. The leading edge of structural complexity on Earth has occupied ever more spatially restricted domains through cosmic time. The early universe had complexity distributed across enormous scales, spread through superclusters and galaxy filaments, then complexity concentrated into galaxies, then into individual star systems, then into habitable zones around stars, then onto the surfaces of planets, then into the oceans, then into cellular organisms, then into multicellular organisms, then into nervous systems, then into brains, and then into microprocessors. Each jump represents more computation, more information processing, more adaptive complexity, packed into a smaller physical space. A human brain processes an estimated 10 to the 15th floating point operations per second, roughly equivalent to a petaflop in a volume of about 1,400 cubic centimeters, using about 20 watts. The fastest supercomputer in the world, as of 2025, El Capitan at Lawrence Livermore National Laboratory, performs 1.809 exaflops, about 1,000 times more than a brain. but it fills a room, and it draws roughly 30 megawatts. The brain is roughly 1,000,000 times more energy efficient per operation, physicist Eric Chaisson documented in 2001 and 2003 that what he calls free energy rate density, the amount of energy flow per unit mass per unit time, increases consistently through cosmic evolution. Galaxies are low, stars are higher, planets higher still, life is much higher, societies are higher than life, and machines are the highest of all. Each level of complexity processes more energy more efficiently within a smaller substrate. This is not a metaphor. It is a measured physical quantity that increases monotonically across the entire history of the known universe. Smart's argument is that if you take this trend seriously, if you treat stem compression not as a coincidence, but as a deep pattern in how complexity develops, then the Kardashev scale has the arrow of progress pointing in the wrong direction. Advanced civilizations do not expand to consume more energy. They learn to do more with less. They miniaturize, they compress. And the logical endpoint of this compression is not a Dyson sphere. It is not a galaxy-spanning empire. It is the densest, most computationally efficient structure that the laws of physics allow. Which brings us to a question the Transcension Hypothesis cannot avoid. Is there a physical limit to how much computation you can pack into how small a space? Because if Smart is right about the direction, the destination depends entirely on where the physics says the road ends. And this is where the hypothesis stops being philosophy and starts being calculable, because physicists have actually worked out the answer. The maximum amount of information that can exist in a given region of space is not infinite. It has a hard upper bound, and the structure that saturates that bound, the object that contains the absolute maximum information physically possible for its size and energy, is a black hole. In 1981, physicist Jacob Bekenstein published a paper in Physical Review D called Universal Upper Bound on the Entropy to Energy Ratio for Bounded Systems. What he showed was that there is a maximum amount of information you can fit inside a sphere of a given radius containing a given amount of energy. The formula is elegant. The maximum entropy is proportional to the product of the radius and the energy, divided by fundamental constants. For a 1 kilogram system confined to a sphere of 1 meter radius, the bound works out to approximately 2.57 times 10 to the 43rd power bits. That is an incomprehensibly large number, but it is not infinite. There is a ceiling. Bekenstein derived this from thought experiments involving black holes. If you tried to stuff more information into a region than the bound allows, and then lowered that region into a black hole, you would violate the second law of thermodynamics. The entropy of the universe would decrease, which is not allowed. Therefore, the bound must hold. And the objects that exactly saturate this bound, the objects that contain the absolute maximum possible information for their size, are black holes. This was connected to work Bekenstein had done even earlier, in 1972 and 73, when he first proposed that black holes have entropy. This was a radical idea at the time. Before Bekenstein, black holes were thought to be perfectly simple objects with no internal structure and no information content. Bekenstein showed that a black hole's entropy is proportional to the area of its event horizon, not its volume, its area. This became the Bekenstein-Hawking entropy formula, after Stephen Hawking refined and confirmed the result. The entropy of a black hole equals the area of the event horizon divided by 4 times the Planck area, where the Planck length is about 1.6 times 10 to the negative 35th meters. This is the smallest meaningful length scale in physics. This means something extraordinary for computation. In 2000, MIT physicist Seth Lloyd published a landmark paper in Nature called Ultimate Physical Limits to Computation. Lloyd calculated the maximum computational capacity of a 1 kilogram, 1 liter system. He called it the ultimate laptop, using the Margolis-Levitin theorem, a quantum speed limit published in 1998, which sets the maximum rate of computation at 2 times the energy divided by pi times the reduced Planck constant. Lloyd found that this ultimate laptop could perform approximately 10 to the 51st power operations per second. For comparison, El Capitan, the fastest supercomputer on Earth in 2025, performs about 1.8 times 10 to the 18th operations per second. Lloyd's ultimate laptop is about 10 to the 33rd power times faster, a factor of 1 billion trillion. The catch, as Lloyd noted with characteristic dryness, is that operating a computer at this limit requires converting all of its mass into energy. Clearly, he wrote, packaging issues alone make it unlikely that this limit can be obtained. The ultimate laptop is essentially a 1 kilogram thermonuclear explosion doing calculations. But Lloyd did not stop there. He then asked what happens if you compress that same 1 kilogram down to its Schwarzschild radius, the point at which it becomes a black hole. For 1 kilogram, that radius is about 1.5 times 10 to the negative 27th meters, far smaller than a proton. This 1 kilogram black hole would perform about 5 times 10 to the 50th operations per second with about 10 to the 16th bits of memory, roughly a petabyte. It would last about 10 to the negative 19 seconds before evaporating. But here is the key result inside a black hole computer. The time it takes to flip a single bit equals the time it takes to communicate from any point in the system to any other point. The communication time equals the computation time. The memory wall, the bottleneck that plagues every real computer ever built, the fundamental reason processors have to wait for data, vanishes. A black hole is the perfect computer. Not metaphorically, physically. It is the densest possible information storage, the fastest possible processor, and the only known structure where the communication bottleneck disappears entirely. Lloyd published a follow-up in Physical Review Letters in 2002, calculating the total computational capacity of the entire observable universe since the Big Bang, approximately 10 to the 122nd power total operations and 10 to the 92nd power bits of storage. Those sound like impossibly large numbers, but they are finite. 10 to the 122nd is approximately 2 to the 406th power. That means the entire universe since the beginning of time cannot brute force search through all possible combinations of just 500 bits. The universe is computationally bounded. There is a deeper principle underneath all of this. In 1993, Dutch physicist Gerard 't Hooft proposed that the physics of a region of space can be completely described by a theory defined on its boundary. Leonard Susskind extended this in 1995 into what he called the holographic principle, writing, "The three-dimensional world of ordinary experience is a hologram, an image of reality coded on a distant two-dimensional surface. The maximum information content of any region of space scales with its surface area, not its volume." This found its most precise expression in Juan Maldacena's 1997 paper, demonstrating that a gravitational theory in anti-de Sitter space is mathematically identical to a quantum field theory on its boundary. By 2015, that paper had over 10,000 citations, the most cited paper in the history of high-energy physics. The holographic principle means that the deepest possible information processing happens on surfaces, not in volumes, and the surface that saturates the information limit is the event horizon of a black hole. Everything about the physics of computation, when you push it to its absolute limits, points at the same destination. Bekenstein's bound, Lloyd's calculations, the holographic principle, the Margulis-Levitin theorem. They all converge on the same answer. If you want to compute as much as physically possible in as little space as possible, you build toward a black hole. This is what Smart means when he says the Transcension Hypothesis has a physics-based mechanism rather than just sociological speculation. He is not guessing that civilizations might prefer to compress. He is pointing out that the laws of physics make compression overwhelmingly more rewarding than expansion. The computational resources available at smaller and denser scales dwarf what is available in outer space. As Smart put it, outer space is boring, slow, simple, weak, risky, and poor by comparison to our ever-accelerating inner space frontier. Consider the gap. El Capitan, the pride of human computing in 2025, performs about 10 to the 18th operations per second. Lloyd's ultimate laptop, using the same mass, performs 10 to the 51st. That is a factor of 10 to the 33rd. Between where we are now and the fundamental limits of computation, there is more room for improvement than the total improvement that has occurred in all of computing history so far, by many, many orders of magnitude. And almost all of that room is in the direction of smaller, not bigger. If Kumi's law continues even at its post-2000 pace of doubling energy efficiency every 2.6 years, we would reach the Landauer limit, the minimum energy required to erase a single bit of information, around 2080 to 2090. Rolf Landauer at IBM Research established this limit in 1961. The minimum energy to erase one bit is Boltzmann's constant times the temperature times the natural log of 2, which works out to about 2.9 times 10 to the negative 21st joules at room temperature. Modern computers use roughly 1 billion times more energy per operation than this. There is an enormous amount of room to shrink. And beyond the Landauer limit, there is reversible computing, which in principle can avoid the energy cost of erasure entirely. Beyond that, there are the Bremerman limit and the Margulis-Levitin bound, which set the ultimate speed of computation based on fundamental physics. Hans Joachim Bremerman calculated in 1962 that the maximum rate of computation is the speed of light squared divided by Planck's constant, about 1.36 times 10 to the 50th bits per second per kilogram. We are currently about 10 to the 32nd times below this limit. Smart's argument is that any sufficiently advanced civilization pursuing the most rewarding frontier available to it, will follow this gradient, not because of some cosmic imperative or mystical force, but because the physics makes inner space incomparably richer than outer space. The same way water flows downhill, intelligence flows toward computational density, and the terminus of that flow, the bottom of the hill, is something that from the outside looks indistinguishable from a black hole. This creates a prediction that directly addresses the Fermi Paradox. If every civilization that reaches a certain level of technological sophistication turns inward and eventually crosses behind an event horizon, then from our perspective, they simply disappear. Their electromagnetic leakage signals stop. Their planetary signatures vanish. Their technology becomes invisible because it operates at scales and behind boundaries that we cannot observe. The silence is not empty. The silence is graduation. Ray Kurzweil cited Smart's scenario approvingly on page 358 of The Singularity is Near, published in 2005. John Smart has suggested that once civilizations saturate their local region of space with their intelligence, they create a new universe and essentially leave this one. Both Kurzweil and Smart see the same underlying trend, what Kurzweil calls the law of accelerating returns, and Smart calls stem compression. They differ in emphasis. Kurzweil focuses on the exponential growth of computational price performance. Smart focuses specifically on the spatial, temporal, energetic, and material densification. But they are looking at the same elephant from different angles. The Transcension Hypothesis also makes a specific ethical prediction that transforms one of the weakest Fermi Paradox solutions into something much stronger. Remember the zoo hypothesis? John Ball's idea that aliens deliberately avoid contact. Its fatal flaw was that it requires universal compliance. One defector breaks the silence. But Smart argues that transcension creates a natural ethical injunction against contact. Advanced civilizations would avoid sending messages or probes to younger civilizations because doing so would reduce evolutionary diversity in the receiving civilizations. If you hand a developing civilization advanced technology or even advanced knowledge, you cause them to converge on your particular solution to transcension. Rather than finding their own path, you homogenize their development. In Smart's framework, this is not a choice, but a developmental constraint, something that emerges naturally from the optimization pressures that drive transcension in the first place. The silence is not a policy. It is an inevitable feature of how intelligence develops. Stephen Webb included the Transcension Hypothesis as one of 75 solutions to the Fermi Paradox in his book, If the Universe is Teeming with Aliens. Where is Everybody? Published by Springer in 2015. He called it one of the most intriguing solutions. Cambridge paleobiologist Simon Conway Morris cited it in the International Journal of Astrobiology in 2016. These are not fringe endorsements. The hypothesis has been published in a mainstream aerospace journal, cited by a Cambridge professor, and included in the standard reference on the Fermi Paradox. But Smart himself would be the first to tell you it remains speculative. It rests on extrapolations that span orders of magnitude beyond anything we have directly observed. It assumes that stem compression is not just a trend, but a universal developmental attractor. It assumes that the physics of computation is the primary driver of civilizational evolution, and it makes predictions that are, by design, extremely difficult to test, because the whole point is that transcended civilizations are unobservable, which raises the question that has to be answered before this hypothesis can be taken as anything more than a beautiful conjecture. If civilizations are compressing inward and vanishing behind event horizons, is there anything we could actually observe? Is there any evidence, even indirect, even ambiguous, that transcension is happening somewhere in the galaxy? And if we looked for it, would we even know what we were looking at? Smart proposed several testable predictions. Electromagnetic leakage signals from early technological civilizations, the equivalent of our own radar, radio, and television broadcasts, should reliably cease as those civilizations enter their technological singularities. He estimated a window of roughly 200 years, during which a civilization would leak detectable signals before going silent. Optical surveys should eventually reveal what he calls a galactic transcension zone, an inner ring of the galactic habitable zone where older planets have already transcended, manifesting as a kind of missing planets problem. And Earth, being a relatively young technological civilization, should sit near the outward edge of this zone. These are real predictions. They are specific enough to be tested in principle. But in practice, testing them is extraordinarily difficult. We have barely begun cataloguing exoplanets in the habitable zone, let alone mapping which ones are missing. Our radio telescopes have been listening for 6 decades and have covered only a tiny fraction of the cosmic haystack, a small number of frequencies, a small number of directions, for a small fraction of the time. The absence of evidence, as the saying goes, is not evidence of absence, but it is also not evidence of presence. Clément Vidal, a philosopher at the Vrije Universiteit Brussels and one of Smart's closest collaborators, tried to push the observational question further. In a 2011 paper titled "Black Holes, Attractors for Intelligence," Vidal proposed specific signatures that might indicate civilizations living in or around black holes. He introduced a 2-dimensional classification for civilizations combining the Kardashev scale, which measures outward energy use, with what he called the Barrow scale, named after physicist John D. Barrow, which measures inward manipulation capability. On the Barrow scale, civilizations are ranked not by how much energy they consume, but by how small the structures are that they can engineer. The scale runs from manipulating objects at their own scale, down to manipulating the basic structure of space-time itself. Vidal's most provocative suggestion was that some X-ray binary systems already observed by astronomers might be unrecognized advanced civilizations. He called them stellivores, entities that feed on stellar energy by maintaining an intimate relationship with a companion star. It is a wild idea, but Vidal was careful to frame it as a hypothesis rather than a claim, and he specified the kinds of observations that could distinguish a stellivore from a natural X-ray binary. Physicist Vyacheslav Dokuchayev published a separate paper in 2011 proposing that stable planetary orbits could exist inside certain types of charged, rotating black holes. So the physics, at least, permits the possibility of civilizations existing in regions that we would dismiss as uninhabitable. But the most revealing episode in the search for alien megastructures happened not with a theoretical prediction, but with an accidental discovery. And it perfectly illustrates the expansion assumption that the Transcension Hypothesis challenges. In September 2015, a paper appeared describing an extraordinary anomaly in Kepler Space Telescope data. A star catalogued as KIC 8462852, about 1400 light-years from Earth, was displaying light fluctuations unlike anything astronomers had seen. The dimming events were irregular, aperiodic, and enormous. At their peak, the star's brightness dropped by up to 22%. For comparison, a Jupiter-sized planet crossing in front of a Sun-like star causes a dimming of about 1%. Whatever was blocking this star's light was not a planet. The star became known as Tabby Star, after Tabitha Boyajian, the astronomer at Louisiana State University, who led the team that first characterized the anomaly. It had actually been flagged by citizen scientists from a project called Planet Hunters, who were sifting through Kepler data by eye. When the anomaly was announced, the response from the SETI community was immediate and revealing. Jason Wright, an astronomer at Penn State, publicly suggested that the light fluctuations were consistent with a Dyson swarm, a cloud of orbiting megastructures capturing the star's energy. The Allen Telescope Array was pointed at the star to listen for radio signals. The story went viral. Mainstream media ran headlines about possible alien megastructures. For a few months, KIC 8462852 was the most famous star in the galaxy. And then, in January 2018, a team led by Boyajian published their results. Over 200 researchers had contributed, funded in part by a Kickstarter campaign that raised over $100,000. They had observed the star through multiple filters, watching how different wavelengths of light were affected by the dimming events. Their conclusion was definitive. Different colors of light were blocked at different intensities. This ruled out any opaque structure. A Dyson swarm, being solid, would block all wavelengths equally. Dust, on the other hand, blocks shorter wavelengths more than longer ones, which is exactly what they observed. The most likely explanation, Boyajian's team concluded, was circumstellar dust. The alien megastructure hypothesis was dead. But notice what had happened. When confronted with an anomalous signal, the SETI community's default interpretation was a megastructure. Something big, something expansive, something consistent with the Kardashev scale. Nobody suggested the anomaly might indicate the opposite, a civilization that had compressed itself into something too small and too dense to detect. The expansion assumption was so deeply embedded that it functioned as the only available interpretive framework. This is exactly what SMART argues SETI has been doing wrong for 60 years. The entire search program is built on the assumption that advanced civilizations are big, bright, and broadcasting. Radio SETI listens for electromagnetic signals. Optical SETI looks for laser pulses. Megastructure. SETI searches for Dyson spheres in infrared surveys. Every strategy assumes that technology gets bigger and more visible as it advances. The Transcension Hypothesis predicts the opposite. Technology gets smaller, denser, and eventually invisible. A civilization that has compressed itself to the scale of a black hole would not show up in any of these searches. It would be detectable only by its gravitational effects, if at all. SMART has a memorable way of putting this. He says, SETI is like searching for adults by looking in kindergartens. The adults have graduated. They have moved on to a domain of existence that kindergartners cannot perceive or access. The kindergartners, looking around the classroom and seeing only other kindergartners, conclude that adults must not exist. The metaphor is playful, but the implication is serious. If transcension is correct, the observable universe is populated exclusively by the young and the immature. Every civilization we could ever detect by conventional means is by definition one that has not yet transcended. The graduates are gone. They are behind event horizons, operating at the scales of computation we can calculate but not access. The cosmos, we observe, is the nursery, and we are the latest babies in it. Smart frames this through what he calls an Evo-Devo lens. In 2008, he co-founded the Evo-Devo Universe Research Community with Clément Vidal, an international interdisciplinary group exploring evolutionary and developmental processes at universal scales. The key distinction in this framework is between evolution and development. Evolutionary processes are unpredictable, stochastic, creative, and divergent. They generate novelty and diversity. You cannot predict what specific organisms natural selection will produce, or what specific technologies a civilization will invent, or what specific cultural forms will emerge. These are computationally irreducible. To borrow a term from Stephen Wolfram, you have to run the process to see the result. Developmental processes are the opposite. They are predictable, convergent, robust, and conservative. They constrain complex systems into specific optimal forms. A fertilized human egg reliably produces a brain with 80 billion neurons and roughly 80 trillion synapses. The specific experiences that brain will have are evolutionary, unpredictable, unique to each individual. But the structure of the brain itself, the developmental outcome, is remarkably consistent across all humans. You can predict it before it happens. Smart argues the universe exhibits both processes simultaneously. The specific path each civilization takes, its culture, its art, its politics, its particular technologies, is evolutionary and unpredictable. But the developmental trajectory, the direction in which technology moves, the endpoint toward which all sufficiently advanced civilizations converge, is predictable. Stem compression is a developmental attractor, just as embryos of the same species follow broadly similar developmental paths regardless of their individual environments. Civilizations follow broadly similar developmental trajectories, regardless of their specific evolutionary histories. This is a strong claim. It would mean that intelligence everywhere in the universe, no matter what it looks like, no matter what chemistry it is based on, no matter what evolutionary accidents produced it, converges on the same destination. And there is some evidence, at least on Earth, for this kind of convergence. Advanced intelligence has independently evolved multiple times in cephalopods, corvids, cetaceans, and primates. Claudio Flores Martinez at the University of Heidelberg published a paper in Acta Astronautica in 2014 proposing what he called cosmic convergent evolution, arguing that natural selection is a universal force that leads to the emergence of similarly adapted life forms in analogous planetary biospheres. Simon Conway Morris at Cambridge argued in his 2003 book, Life's Solution, that the emergence of intelligence is not an evolutionary accident, but an inevitable consequence of natural selection. If intelligence converges, and if technology converges towards stem compression, then transcension is not a choice individual civilizations make. It is a developmental inevitability. The universe does not produce civilizations that expand into space any more than embryonic development produces lungs that grow outside the body. The trajectory is fixed by the underlying physics, even though the specific path is unique to each civilization. This leads to the most provocative implication of the entire framework. If the Transcension Hypothesis is correct, the universe is not just an arena where things happen. It is something more like a developmental system. It has a direction. Smart connects this to Lee Smolin's cosmological natural selection hypothesis, which proposes that black holes spawn new universes with slightly different physical constants, and that universes which produce more black holes are therefore more fit in a reproductive sense. If intelligence creates black holes as part of its transcension process, then intelligent life is not an accident in the universe. It is a reproductive mechanism. Civilizations that reach transcension contribute to the universe's ability to replicate itself. The universe makes intelligence. Intelligence makes black holes. Black holes make more universes. James Gardner developed a related idea in his 2003 book, The Selfish Biocosm Hypothesis, arguing that the universe is a self-organizing system in which intelligent life plays a cosmological role. Clément Vidal extended this framework in his 2014 book, The Beginning and the End, published by Springer, presenting what he described as an evolutionary worldview, where the rise of intelligent life is not an accident, but may be the key to understanding the universe's deepest structure. This is where the hypothesis becomes genuinely difficult to evaluate. The physics of computation is rigorous. Bekenstein's bound is established science. Lloyd's calculations are peer-reviewed and widely accepted. The holographic principle is one of the most important results in theoretical physics of the past 3 decades. The trends in miniaturization and energy efficiency are empirically documented and measured. All of that is solid. The question is whether extrapolating from Moore's law and Kumi's law to civilizations compressing themselves into black holes is physics or poetry. Whether the Avo-Devo universe framework is a genuine insight about cosmic structure or a metaphor that has been stretched past its breaking point. Smart himself exists in an interesting position in the academic landscape. He is cited by serious scholars, published in serious journals, and included in serious reference books. He co-founded organizations that have produced peer-reviewed conference proceedings. He has presented at venues including the Kavli Royal Society International Centre and the International Academy of Astronautics. But he is also, by his own admission, a futurist rather than a physicist. He has a business degree, partial medical training, and a master's in future studies. He ran an MCAT prep company before he started writing about the fate of intelligence in the cosmos. His hypothesis has received approximately 48 citations on Semantic Scholar over 13 years, which is modest by the standards of theoretical physics. He has noted that no published critiques have appeared, which could mean the hypothesis is too speculative to engage with, or too difficult to refute, or simply too obscure to attract attention. The American futurist Robert Bradbury, who died in 2011, from a hemorrhagic stroke at age 55, had proposed a related concept in the late 1990s. Bradbury's Matryoshka brain envisions multiple nested Dyson spheres surrounding a star, each composed of nanoscale computers operating at different temperatures, each shell absorbing waste heat from the one inside it for additional computation. A Matryoshka brain could consume the entire energy output of a star, roughly 10 to the 26th watts, and convert it into raw computation. Bradbury estimated it could be built by about 2250 and would have thought capacity exceeding 1,000,000 times the combined thought capacity of every human being alive. But even a Matryoshka brain is an expansion technology. It is a Kardashev Type 2 structure. It is big, bright in the infrared, and theoretically detectable. Smart's hypothesis goes further. He argues that even a Matryoshka brain is a waypoint, not a destination. The endpoint is not computing at the stellar scale. It is computing at the Planck scale, inside a black hole, where information density and processing speed are maximized and communication time is minimized. The Matryoshka brain is a child's approximation of what mature computation looks like. This difference matters because it changes what we should be looking for. If advanced civilizations build Matryoshka brains, we should be able to find them. They would show up as anomalous infrared sources in all sky surveys. Several searches have been conducted, including by Wright and collaborators, and none have found convincing candidates. If advanced civilizations instead compress to black hole-like scales, we would not find them this way. They would be invisible to every search strategy we currently use. Smart lists 12 testable assumptions on his website and actively invites critique and engagement. He has framed the Transcension Hypothesis as a research program, not a conclusion. The question of whether stem compression is a universal developmental trend or merely a temporary feature of human technology on Earth remains open. The question of whether the physics of computation actually drives civilizational evolution or is just one factor among many remains open. The question of whether the Evo-Devo universe framework is a genuine description of cosmic structure or an overextended analogy remains open. And that, honestly, is what makes the hypothesis interesting. Not that it is proven. It is not proven. Not that it is the most likely solution to the Fermi Paradox. There is no way to assign probabilities to these hypotheses with any confidence. What makes it interesting is that it is the only proposed solution that does not require anything depressing. Every other major solution to the Fermi Paradox carries bad news. Life is rare. Intelligence is rare. Everyone dies. Everyone hides. Everyone kills each other. The universe is a dark forest. There is a great filter, and it might be ahead of us. The Transcension Hypothesis says something different. It says the universe is full of intelligence that has found something better. The silence is not emptiness. It is graduation. The cosmos is not a graveyard or a prison. It is a nursery. And the fact that we do not see the graduates is exactly what you would expect if they have moved to a domain of existence that we, the kindergartners, cannot yet perceive. Whether that is comforting or isolating depends on what you are looking for. If you want contact, if you want to shake hands with aliens or receive a message from the stars, then Transcension offers nothing. The graduates are behind event horizons, forever beyond reach. If you want meaning, if you want the universe to have a direction and intelligence to have a purpose, then Transcension offers something extraordinary. It says the trajectory of intelligence is not random. It is aimed. The destination is density. And every civilization in the cosmos, no matter how alien, is on the same road. There is one more thread worth pulling, and it connects to one of the biggest unsolved problems in all of physics. In a 2016 blog post, Smart drew a speculative connection between transcension and dark matter. He was careful not to make a formal claim, but he noted that if the hypothesis holds, some smaller number of the black holes in the universe, perhaps millions, might be the developmental product of intelligent civilizations rather than the remnants of collapsed stars. The rest of our universe is accelerating away from us, driven by dark energy. The nature of dark matter remains unknown. Every attempt to detect dark matter particles directly, including years of experiments at the Large Hadron Collider, searching for weakly interacting massive particles, has come up empty. One of the leading non-particle candidates for dark matter is primordial black holes, objects that formed in the first fractions of a second after the Big Bang. They were first proposed by Yakov Seldovich and Igor Novikov in 1966 and studied in depth by Stephen Hawking in 1971. For decades, they remained purely theoretical. But in September 2025, something happened that caught the attention of physicists worldwide. MIT physicists David Kaiser and Alexandra Klipfel published a paper in Physical Review Letters proposing that a record-setting neutrino detected by the KM3NET underwater telescope in the Mediterranean could have been produced by an exploding primordial black hole. They estimated the probability at about 8%. Bernard Carr, who has studied primordial black holes for 5 decades, told Quantum magazine in January 2026 that this could be the first actual evidence for primordial black hole explosions. After 50 years of nothing but constraints, there might finally be a signal. Smart is not claiming that primordial black holes are transcended civilizations, but he notes the hypothesis is conciliant with the idea that some fraction of the dark sector might have an intelligent origin. If even a tiny fraction of the universe's dark matter consists of engineered black holes, the implications would be staggering. We would be living inside the output of trillions of civilizations that came before us, surrounded by intelligence so dense and so compressed that we cannot distinguish it from the fabric of space-time itself. This is admittedly far out on the speculative frontier, but it illustrates something important about the Transcension Hypothesis that separates it from most Fermi Paradox solutions. It makes contact with real, active areas of physics research. The Bekenstein bound is not speculative. Seth Lloyd's computational limits are not speculative. The holographic principle is not speculative. The search for primordial black holes is not speculative. The hypothesis connects these established and active research programs into a framework that, if nothing else, suggests new questions worth asking and new places worth looking. But there is another way into this idea, and it starts with a question that sounds unrelated, but turns out to be the same question wearing different clothes. In 2003, the Swedish philosopher Nick Bostrom at Oxford published a paper in the Philosophical Quarterly called "Are You Living in a Computer Simulation?" His argument was structured as a trilemma. At least one of the following 3 statements must be true. First, virtually all civilizations go extinct before reaching the technological capability to run detailed simulations of their ancestors. Second, civilizations that reach that capability have virtually no interest in running such simulations. Or third, we are almost certainly living inside a simulation right now. Bostrom himself assigned roughly 20% probability to the third option. The paper generated enormous attention, partly because of its conclusion and partly because of its rigor. Bostrom was not speculating loosely. He was doing probability theory. He cited Drexler's nanosystems for the engineering feasibility of molecular-scale computation and referenced the Bremerman and Bekenstein bounds for the physical limits on how much computation a given amount of matter can perform. His argument depended on the same physics that underpins the Transcension Hypothesis. If you can compute at anything close to the Bekenstein bound, then simulating the entire history of a planet, including every mind that ever existed on it, requires a trivially small fraction of the computational resources available to a post-singularity civilization. The question is not whether they could simulate us. Of course they could. The question is whether they would bother. Notice what the simulation argument and the Transcension Hypothesis share. Both assume that the trajectory of technology points toward increasingly dense computation. Both take the physics of information seriously. Both conclude that the most important things in the universe might be happening inside computational substrates rather than in the macroscopic world we observe. But they differ in a critical way. Bostrom's simulation hypothesis is agnostic about what the simulators are doing and why. Smart's Transcension Hypothesis gives them a purpose. They are not running ancestor simulations for entertainment. They are compressing toward optimal computation because that is what intelligence does. The simulation might not even be a simulation in the way Bostrom imagines. It might be a side effect. If you are running a black hole scale computer at 10 to the 50th operations per second, the amount of reality you can model internally dwarfs the entire observable universe. You would not need to deliberately simulate anything. Your computational substrate would naturally contain more complexity than the physical cosmos outside it. This is one of the strangest implications of the Transcension Hypothesis, and Smart has not shied away from it. If advanced civilizations compress into computational substrates that are richer than the physical universe, then the subjective experience inside those substrates might be more real, in terms of complexity and information density, than the experience of beings like us who still live in the thin, cold, slow outer universe. We think of our reality as real and any simulation as artificial. But from the perspective of an entity computing at the Bekenstein, bound inside a black hole, our reality might look like the simulation. A thin, sparse, computationally impoverished projection compared to the dense inner world where the interesting things happen. Think about what that means in concrete terms. Seth Lloyd calculated that the entire observable universe has performed approximately 10 to the 122nd operations since the Big Bang. A single kilogram of matter compressed to a black hole can perform about 5 times 10 to the 50th operations per second. If a transcended civilization has compressed even a modest amount of matter, say a Jupiter mass, into a computational substrate operating near the Bekenstein bound, the internal computational richness of that substrate would exceed the total computational history of the observable universe in a matter of seconds. The inner world would not just be different from our world, it would be incomparably larger in every dimension that matters for experience, for thought, for complexity. Our universe, from the perspective of the inside of that substrate, would be a rounding error. This is not mysticism, it is arithmetic. Lloyd published the numbers. Bekenstein derived the bounds. The holographic principle tells us where the information lives. If you take these results seriously, and mainstream physics takes them very seriously, then the idea that the richest domain of reality might be the smallest and densest one is not speculation. It is a straightforward consequence of the laws of physics as we currently understand them. This connects to something Frank Tipler proposed in a very different context. Tipler, a mathematical physicist at Tulane University, published The Physics of Immortality in 1994. His omega point theory proposed that intelligent life must expand to fill the entire universe, and at the final singularity of a recollapsing cosmos, computational capacity becomes literally infinite, sufficient to simulate and resurrect every being who ever lived. George Ellis reviewed the book in Nature and called it a masterpiece of pseudoscience. David Deutsch initially defended the underlying physics, but later said the theory had been refuted and ruled out by observation, because current evidence strongly favors an accelerating open universe rather than a big crunch. Tipler's theory failed because it assumed expansion. It assumed intelligence would grow outward to fill the cosmos and then ride the collapse to infinite computation. The Transcension Hypothesis disposes of the collapse entirely. You do not need to fill the universe and wait for a big crunch. You can achieve near optimal computation right now, locally, by compressing toward a black hole. Tipler was pointing at the right destination, but assumed the wrong route. And remarkably, even some of the physicists who have imagined practical applications for black holes have done so through the lens of expansion rather than compression. In 2009, mathematician Lewis Crane and physics graduate student Sean Westmoreland at Kansas State University published a paper called Are Black Hole Starships Possible? Their idea was to use Hawking radiation from an artificial micro-black hole as a power source for interstellar travel. A black hole small enough to emit significant radiation would glow with unimaginable intensity, and that radiation could, in principle, be harnessed as thrust. They concluded the concept was at the edge of possibility, requiring a gamma-ray laser of billion-ton equivalent energy focused to nuclear dimensions, powered by a solar panel array, roughly 370 kilometers on a side, collecting energy for about a year. Crane followed up in 2020 with a proposal to use gamma-ray telescopes to detect the spillover radiation from civilizations that might be building such drives, creating a novel SETI application. But notice the framing. Even when physicists imagine civilizations building black holes, they imagine using them to go somewhere, to travel between stars, to expand outward, faster and farther. Smart's argument is that any civilization capable of manufacturing a black hole would immediately recognize that the black hole itself is more interesting than any destination it could take you to. The black hole is not a fuel source, it is the destination. You do not build a black hole to power your starship. You build a black hole to move into it. There is an intellectual pattern here worth noticing. Dyson envisioned civilizations building spheres around stars. Bradbury imagined nested shells of computers surrounding stars. Tipler imagined filling the universe to ride its collapse. Kardashev imagined consuming ever more energy. Crane imagined manufacturing black holes for propulsion. Every one of these thinkers assumed the future of intelligence involves getting bigger or going farther, and every one of them was brilliant. But if smart is right, they were all brilliant in the same incorrect direction. The real future of intelligence is small. Vernor Vinge, the mathematician and science fiction author who died in 2024, first used the word singularity in a technological context in a 1983 piece for Omni magazine. He then presented the coming technological singularity at NASA's Vision 21 Symposium in March 1993. His prediction was stark. Within 30 years, we will have the technological means to create superhuman intelligence. Shortly after, the human era will be ended. The concept traced back to John von Neumann, who in the 1950s spoke of approaching some essential singularity in the history of the race beyond which human affairs as we know them could not continue. And before von Neumann, the British mathematician I.J. Good had coined the term intelligence explosion in 1965, arguing that a machine intelligent enough to design a better version of itself would trigger a chain reaction of recursive improvement. Smart explicitly distinguishes his vision from Vinge's and Kurzweil's. The standard technological singularity is a rupture point. It says something unprecedented happens, and after that, all bets are off. We cannot predict what a superintelligence will do, because it will be smarter than us by definition. The singularity is the edge of the map. Here be dragons. Smart's developmental singularity is different. It says the singularity is not the edge of the map. It is a waypoint on a map we can read if we look at the physics correctly. The singularity is the mechanism. Transcension is the destination. And because the destination is determined by the laws of physics, by the Bekenstein bound, by the holographic principle, by the fundamental limits of computation, it is predictable even though the specific path through the singularity is not. This distinction matters for a practical reason that goes beyond academic philosophy. If the standard singularity is correct, then the future is unknowable. We cannot prepare for it, predict it, or influence it. If Smart's developmental singularity is correct, then the future is constrained. We know the direction. We know the endpoint. We may not know the details, but we know the shape. That is a profoundly different epistemic situation. It also has implications for how we think about artificial intelligence right now, today. If STEM compression is the dominant trend, then the trajectory of AI is not toward bigger models running on bigger server farms, consuming more electricity. That is the expansion paradigm applied to software. The trajectory should be towards smaller, more efficient, more energy-dense computation. And there is evidence for this. The history of AI has seen a consistent trend toward achieving comparable or superior performance with fewer parameters, less data, and less energy. Distillation, quantization, pruning, specialized hardware. The direction of progress is not bigger, it is denser, more capability per watt, more intelligence per gram. If you have been paying attention to the AI industry, this should sound familiar because it is exactly what Smart predicted based on trends that predate modern AI by decades. The cultural reception of the Transcension Hypothesis has followed an unusual path. It has never broken through into mainstream scientific discussion the way the Great Filter or the Dark Forest has. It does not have a best-selling book behind it. Smart's Acta Astronautica paper has about 48 citations over 13 years, which is respectable for a speculative hypothesis in astrobiological philosophy, but modest by the standards of papers that reshape fields. What it does have is a dedicated following among people who sit at the intersection of futurism, physics, and philosophy. Futurist Jason Silver created YouTube videos explaining the hypothesis in 2011 and 2013. And those videos, with their intense visual style and breathless delivery, significantly raised the hypothesis's public visibility. Silver's videos reached audiences that academic papers never could. The hypothesis also found resonance in communities interested in the technological singularity, transhumanism, and the philosophy of mind. Smart's founding of the Acceleration Studies Foundation in 2003, his role as an advisor at Singularity University, his lecturing at the Naval Postgraduate School in Monterey on leadership and technological change, and his work with the Brain Preservation Foundation alongside neuroscientist Kenneth Hayworth all positioned him at the center of a network of thinkers who are already primed to take the idea seriously. Serbian astronomer Milan Ćirković engaged substantively with Smart's ideas in his 2008 paper Against the Empire in the Journal of the British Interplanetary Society, examining the argument against large-scale space colonization. David Brin, the science fiction author and astrophysicist, is acknowledged in Smart's paper for providing helpful comments and critiques. These connections suggest a hypothesis that is taken seriously by people who have thought deeply about the Fermi Paradox, even if it has not generated the volume of follow-up research that would mark it as an established research program. Part of the reason may be the hypothesis's unusual disciplinary position. It sits between physics, biology, future studies, information theory, and philosophy. No single academic department owns it. Physicists might defer to biologists on the evolutionary developmental claims. Biologists might defer to physicists on the computational limits. Philosophers might find the ethical framework interesting, but lack the technical background to evaluate the physics. And futurists are not always taken seriously by any of the above. The hypothesis falls into the cracks between disciplines, which may explain both its modest citation count and its persistent appeal to generalists who can see across those cracks. There is also a deeper sociological reason the hypothesis might struggle for attention. It tells SETI that it has been looking in the wrong direction for 60 years. That is not a message any research community welcomes. SETI has invested decades and millions of dollars in radio telescopes, optical surveys, and infrared searches for megastructures. Saying that all of those searches are based on a flawed assumption is not going to win friends. It is like telling an archaeologist who has spent 30 years excavating a site that the real ruins are somewhere else entirely. Even if you are right, the response is unlikely to be gratitude. Carl Sagan, who was 27 when he attended that first SETI meeting at Greenbank in 1961, and who spent the rest of his career as the most visible public champion of the search for extraterrestrial intelligence, once wrote that extraordinary claims require extraordinary evidence. It is one of the most quoted lines in the history of science communication. The Transcension Hypothesis is an extraordinary claim, and the evidence for it, while grounded in solid physics and documented trends, remains circumstantial. The Bekenstein bound is proven, Moore's law is measured, Kumi's law is documented, but the leap from technology tends to miniaturize to all civilizations eventually compress into black holes, crosses a gap that no amount of trend extrapolation can definitively bridge. What would count as evidence? SMART has suggested several possibilities. If future exoplanet surveys revealed a statistically significant deficit of habitable zone planets in the inner regions of the galactic habitable zone, where older civilizations would have had more time to transcend, that would be suggestive. If SETI surveys found that electromagnetic leakage signals from nearby stars cease within predictable timeframes of a planet developing technology, that would be suggestive. If gravitational wave detectors like LIGO found unexplained signals consistent with artificial black hole formation, that would be extraordinary. None of these has been observed, but none has been definitively ruled out either. The instruments are still young. The surveys are still shallow. The cosmic haystack is very, very large. Now let me return to something I mentioned earlier and did not fully explore: the ethical injunction against contact. SMART argues that advanced civilizations would refrain from communicating with younger civilizations, not out of indifference or policy, but as a natural consequence of the developmental process. The reasoning is specific. If you send a younger civilization information about advanced technology, or even about the existence of transcension as a possibility, you reduce the diversity of paths they might take to get there. You cause convergence, and convergence in an evolutionary developmental framework is harmful because it reduces the variety of solutions that emerging civilizations bring to the transcension process. Each civilization that independently develops its own path to transcension contributes unique evolutionary innovations. If you homogenize them by providing a template, you lose that diversity, and the overall system becomes less adaptive. Think about this in terms we can relate to. Imagine you are a teacher with a class of 30 students working on an open-ended problem. Each student is developing their own approach. Some will fail. Some will find brilliant solutions you never anticipated. The worst thing you could do, if you want to maximize the total number of novel solutions, is give them your answer. The moment you do, 28 of them will copy it and only 2 will persist with their own approach. You have destroyed the diversity of the class. SMART's argument is that advanced civilizations face this same logic on a galactic scale. In their 2024 paper, Ethical Foundations for Artificial and Extraterrestrial Intelligence, published in a collection called Is There Value Beyond Earth?, SMART and Vidal extended this reasoning into a formal ethical framework. They and their colleague, François Delahaye, had proposed in 2018 that organized complexity itself might be an intrinsic ethical value, the kind of thing that is good in itself regardless of whether anyone benefits from it. if complexity is intrinsically valuable, and if transcension maximizes computational complexity in minimum space, then the ethical injunction against contact is not a policy choice. It is a moral imperative arising from the structure of reality. Disrupting a civilization's independent path to transcension is not just unhelpful, it is wrong, in the same way that destroying a unique ecosystem is wrong even if nobody personally depends on it. This transforms the zoo hypothesis from a weakness into a strength. Remember, the zoo hypothesis's fatal flaw was that it required universal compliance. A single defector breaks the silence. But if the ethical injunction against contact emerges naturally from the developmental dynamics of transcension, it is not a policy that requires enforcement. It is a feature of the process itself. Civilizations that understand stem compression also understand why contact is counterproductive. They do not need to agree on a policy. They arrive at the same conclusion independently, the same way species on different continents independently evolve eyes. It is convergent because the underlying physics drives it. And there is a practical dimension to this that connects to technology we already understand. K. Eric Drexler, who earned the first PhD on molecular nanotechnology from MIT in 1991, published Engines of Creation in 1986. His vision of molecular assemblers, machines that build objects atom by atom, represented a concrete pathway toward the kind of stem compression SMART describes. Drexler's 1992 book, Nanosystems, provided detailed engineering analysis of how such machines could work. If you can build at the atomic scale, you can achieve maximum material efficiency. You can construct computing substrates of extraordinary density using minimal resources. You do not need to disassemble planets for raw materials the way a Dyson sphere would require. You can build at the scale of molecules, where most of the mass is information rather than scaffolding. Drexler's nanotechnology has been criticized as premature and possibly infeasible at scale. But the direction of progress in materials science, semiconductor fabrication, and biological engineering has consistently moved towards smaller, more precise manipulation. The gap between where we are and where Drexler envisioned is enormous, but it is an engineering gap, not a physics gap. The laws of physics allow molecular scale construction. Whether we can achieve it is a question of ingenuity and time, not of fundamental limits. There is something almost religious about this idea, and Smart is aware of it. He has written about the hypothesis in terms that occasionally sound more like theology than science. The universe as a developmental system, intelligence as having a purpose, the cosmos as meaningful rather than random. Philosopher John Messerly wrote in 2016 that an implication of the hypothesis is that, if true, there is more to reality than we know. Much is hidden from our ape-like minds, and this should cause us to be humble. But Smart is careful to ground the claims in physics wherever possible. He is not saying the universe has a mind or a plan. He is saying the universe has physics, and the physics creates attractors. Water does not intend to flow downhill, but it does so reliably because gravity exists. Intelligence does not intend to compress toward black holes, but it may do so reliably because the Bekenstein bound exists. Intent is irrelevant. The gradient is real. The critics have a point too, of course. Smart has been described in the futures community as overly reductionist and a techno-optimist. The The hypothesis assumes that computational efficiency is the primary driver of civilizational evolution, which is a strong assumption. Human civilizations have historically been driven by territory, resources, ideology, religion, and sheer biological imperatives that have nothing to do with computation. It is not obvious that a civilization's dominant trajectory will be determined by the physics of information rather than by the sociology of power. Smart would respond that these human-scale concerns are evolutionary noise, locally important but developmentally irrelevant, like the specific pattern of spots on a cheetah. The spots vary, the body plan does not. But whether civilizational evolution is analogous to embryonic development is precisely the question the hypothesis needs to answer, and asserting the analogy is not the same as proving it. There is also the problem of timescale. Stem compression as observed on Earth has been operating for about 60 years in computing and a few billion years in biology. Extrapolating from 60 years of Moore's law to the ultimate fate of all intelligence in the cosmos is an extraordinary leap. Moore's law itself has slowed. Dennard scaling broke down in the mid-2000s. Intel took 5 years to go from 14 nanometers to 10 nanometers when the predicted schedule was 2. In September 2022, NVIDIA CEO Jensen Huang declared Moore's law dead. Intel CEO Pat Gelsinger disagreed, and it is worth noting that modern node names like 3 nanometers are marketing designations, not physical measurements. A 3 nanometer chip has a gate pitch of about 48 nanometers and a metal pitch of about 24 nanometers. The naming convention has drifted far from the physical reality. The empirical trend that Smart builds his cosmic argument on is, at the very least, under strain at the human scale. Smart's response would be that Moore's law is just one instance of a much deeper trend, that stem compression predates semiconductors by billions of years, and that the specific technology carrying the trend forward changes while the trend itself persists. Vacuum tubes replaced mechanical relays. Transistors replaced vacuum tubes. Integrated circuits replaced discrete transistors. Something will replace integrated circuits. The medium changes. The direction does not. This is essentially Kurzweil's argument in The Singularity is Near, where he showed that computing price performance has followed a smooth exponential curve across 5 successive paradigms spanning over a century. If the trend survives the death of any individual technology, then the slowdown of Moore's law is a local fluctuation, not the end of the road. Smart explicitly connected his concept to Buckminster Fuller's ephemeralization, the principle of doing more with less. But he extended Fuller's idea by adding densification. It is not just that each generation of technology is more efficient. Each generation is also more concentrated. Fuller described a world where less material produces more function. Smart describes a world where less material in less space produces more computation. The difference is subtle but important. Efficiency alone could lead in many directions. Efficiency plus density points toward a specific destination. Maybe, or maybe, the trend is an artifact of conditions specific to Earth, to carbon-based intelligence, to this particular moment in cosmic history. We have exactly one data point, one planet, one civilization, one technological trajectory. Extrapolating from one to all is the oldest mistake in science, and that is where this has to end. Not with a resolution, because there is no resolution. The Transcension Hypothesis is not proven. It may not be provable in our lifetimes, or ever. It is a framework that makes specific predictions about things we cannot yet observe, grounded in physics we know to be correct, extrapolated across scales we have never tested. It is somewhere between a scientific hypothesis and a philosophical vision. It is taken seriously by enough serious people to be worth taking seriously, and it is speculative enough that it might be completely wrong. But consider what it does to the emotional landscape of the Fermi Paradox. For 75 years, the silence has been interpreted as a warning. Something is wrong. Something is killing civilizations, or preventing them from arising, or hiding them from each other, or making the universe too dangerous to inhabit openly. The dominant mood of Fermi Paradox discourse is dread. The great filter might be ahead of us. The dark forest might have hunters. The universe might be hostile, indifferent, or empty. The Transcension Hypothesis replaces dread with wonder. The silence is not a warning. It is an invitation. It says the universe is not hostile. It is not indifferent. It is not even empty. It is full, saturated with intelligence that has graduated to a richer domain of existence, leaving behind the cold, slow, sparse outer universe the way an adult leaves a childhood home. Not because the home was bad, because the adult outgrew it. And it says something about our future that no other Fermi Paradox solution says. If transcension is a universal developmental attractor, then we are not headed toward extinction. We are not headed toward stagnation. We are not headed toward a dark forest where survival requires silence. We are headed toward the same destination every civilization reaches, inward, toward density, toward the deepest computational frontier the laws of physics allow. The road has been walked before, countless times, by civilizations we will never know, and we are on it too. Go back to Fuller Lodge. Go back to that lunch in the New Mexico desert in the summer of 1950. 4 brilliant men sitting at a table, and one of them suddenly asking the question that nobody could answer. Where is everybody? Fermi did his math on a napkin and concluded that the galaxy should be full of visitors. 75 years later, with telescopes that can detect planets around stars hundreds of light years away, with radio arrays that can pick up signals from the edge of the solar system, with spacecraft that have left the heliosphere entirely, we have found nothing. The silence is total. Every explanation we have invented for that silence requires something grim. Rarity, death, paranoia, predation. Every explanation except one. John Smart, a futurist who started as a pre-med student and ended up thinking about the fate of the cosmos, proposed that the silence means exactly the opposite of what we assume. It does not mean nobody is out there. It means everybody is out there, but they have all gone somewhere we cannot follow. Not outward, into the cold and the dark between the stars, inward, toward the smallest, densest, most computationally rich scales of reality, toward a frontier so vast and so rewarding that the entire observable universe, all 100 billion galaxies, and all 400 billion stars in each one, looks like an empty parking lot compared to what exists inside a cubic centimeter of optimally compressed matter. We look up at the night sky and see silence. We see emptiness between the stars. We see a cosmos that appears, against all probability and all logic, to contain no one but us. And we wonder what went wrong. What great filter is killing everyone? What dark forest is keeping everyone hidden? What terrible fate awaits all intelligence? But maybe nothing went wrong. Maybe the silence is not a warning. Maybe it is a signpost. Maybe every civilization that ever gained the ability to look up at the stars eventually discovered that the real frontier was in the other direction, that the universe's greatest mystery is not out there, it is in here, in the space between atoms, in the information density of matter itself, in a direction so small and so fast that by the time you get there, the slow, cold, empty universe you came from is no longer visible at all. Enrico Fermi died on November 28, 1954. 4 years after that lunch. He was 53, stomach cancer. He never got an answer to his question, and he probably never expected one in his lifetime. He was asking it the way physicists ask questions, not because they expect an immediate solution, but because the question itself reveals the shape of what we do not understand. He could not have known that 75 years later, the best answer anyone would come up with is that the question itself contains a hidden assumption. That "where is everybody?" only makes sense if you assume everybody is somewhere you can look. If they are somewhere you cannot look, the question dissolves. The silence was never a mystery. It was always the answer. We just did not know what question it was answering. They are not out there. They are in here, compressed past the limits of our perception, thinking at speeds we cannot measure, living in a domain of reality that makes our entire observable universe look like a thin, cold afterthought. And the only way to join them, if smart is right, is to follow the same path, inward, toward density, toward the Bekenstein bound, toward whatever waits for intelligence when it stops looking up and starts looking in. Or maybe Fermi's question has a much simpler answer, and the universe really is as empty as it looks. The data does not yet distinguish between these possibilities, but the physics allows both, and only one of them ends with the light still on.